Hey, it's me, Destin. Welcome back to Smarter Every Day. Here's the deal. I'm in a super weird place in life, right? I've got 4 kids. I'm an engineer. I've got this YouTube thing. I give talks, but my channel name is Smarter Every Day. I've been wanting to go back and get a PhD for years, but it's never felt right. It feels right now. I met a guy. His name is Dr. Kavan Hazeli. We click. We're on the same wavelength. I'm going to get a PhD, and there's more to it than that. Dr. Hazeli applied for a National Science Foundation grant. Over a 5-year period, he's got $1 million. And he's asked me if I'd come work with him as a part of my PhD, I could help work with transfer students for research. And the research is incredible. Like, that's the thing about the University of Alabama in Huntsville, right? This is a school located right next to Marshall Space Flight Center. You got all these Army organizations nearby. There's a ton of research that happens at UAH. So here's the deal. In this video, I'm going to show you 3 research programs that are actively looking for undergraduate transfer students. Topic number 1, 3D lattice structures printed by NASA. We're testing the strength. Check out Dr. Hazeli's lab. I'm about to film Dr. Hazeli when he doesn't expect it. Dr. Hazeli.
Hey.
Okay, so this is Dr. Hazeli, and he's in charge of the lab here. It's what do we call this? It's the
So what we do here, basically, we are learning about material behavior. So we try to understand how materials react with different environments. Could be impacts, could be loading, could be just cycling the materials. And the entire idea is learn from the material behavior and inform manufacturing.
So Dr. Hazeli showed me this, and he was like, "Are you interested in getting a PhD?" And I said, "Yes," because what do you call this?
So we call them lattice structures. Basically, we remove the mass from materials by carefully printing them out. So the idea behind them is make the materials light yet strong enough to withstand a lot of pressure and lot for different environments. So we have this set of the topology which was given to us by NASA. Our ultimate goal is to optimize the topology.
Which one is strongest?
For quasi-static compression test, Octatraz is the strongest one.
Well, what about for impact? Is it different?
We haven't tried yet, so we wanted to do it today, maybe.
Is it possible that impact's different than quasi-static?
Yes, possible.
Why?
Because the mechanisms by which material deform at high strain rate is different than quasi-static.
Okay, Andrew is about to do his first shot, and it's dodecahedron, right?
Yes.
Right. Dodecahedron. So the way this works is there's this large piston over there. He pressurizes the piston, slams it into this long rod. This rod is going to impact the sample right there. And so you can get the input and output energy of this impact, and you can see how much energy that particular sample absorbed.
Okay, 3, 2, 1. 3, 2, 1.
So it got squished. Did like perfectly flat?
Yeah.
Let me see.
Wait, nuh-uh.
And it's hot.
It's hot?
Yeah. So you cannot dissipate a lot of heat when deformation is very fast. So that amount of temperature stored in the material, this was very hot.
So it's hot right now?
Yeah.
I feel it? Oh, it sure is. So that was dodecahedron.
Right.
What are you going to do next?
So the next is a rhombic dodecahedron.
Sweet, let's do it. This is a big deal. Like, everybody knows you can 3D print metals, but this problem is very difficult. For example, stress equal force divided by area, but what is the cross-sectional area? Do you treat it like a bulk material? Do you measure the cross-section of each individual leg on the topology? What is the angle? How does it matter? Blah, blah, blah. There's a ton of stuff. We're measuring the overall strain of the material. We're equating that to a stress. This is the future of metal. Like, we are figuring out how to work as humans with 3D printed structures, and it's fantastic. So that's one option for research. Another one is Dr. Gabe Hsu, who's working at the Plasma Electrodynamic Research Lab. This is incredible stuff. Okay, so Dr. Hsu is just, I like walk in the room and he's showing me an ion thruster. That's how it rolls here.
The planned use is eventually want to develop it for small satellites, CubeSats. Maybe not 1U, say 3U, 9U CubeSats to allow them to have orbit maneuvering capabilities.
So what kind of ISP would you see from something like this? I've played a little bit of Kerbal Space Program.
For very small ones like these ICs, you may be looking at, I'll say like 1,000 seconds.
Whoa.
Definitely startup transients.
Startup transients? Are you not entertained? I walk in and the man's firing an ion thruster and he's like, oh, whatever, just startup transient, it's not a big deal. What? What's happening?
Dr. Shu just made it work like MacGyver, only ion propulsion. Is that pretty much what happened?
Like MacGyver. I call MacGyver, you know.
Oh, come on, just embrace it.
So there is a electromagnet wrapped around the thruster, which we're about to turn on. The goal of electromagnet is basically to generate a magnetic field inside to trap the electrons and to reduce the electron current to the anode, basically. So we're trying to control the amount of current that the anode is seeing.
Really? So is thrust directly proportional with current?
Thrust is proportional, kind of. It's proportional to the acceleration voltage and how many ions come out, which you can sort of say is current, and it just died.
So to be clear, Dr. Shu is interested in getting research assistants at the undergrad level, which would be what these students are doing here. So they could basically come work with you and develop ion propulsion.
Yeah, we're going to different propulsion plasma projects.
That's awesome.
I know, right? Is that awesome or what? Okay, the last lab, I've actually featured this on Smarter Every Day in the past. It's called the Atom Lab. They are researching how butterfly wings work, and they're doing it with these really cool cameras that can calculate the position of a butterfly wing just by putting a reflector on his wing when he flies.
Okay, I'm in the Atom Lab with Dr. Kang, and you get to do some pretty cool stuff with butterflies, right? Mm-hmm. What do you do?
So we are interested in butterfly flights, and in particular the monarch butterflies, because they are known for their migration distance, which is the longest among insects. No one really understands how they are able to make that distance, which can be as long as 4,000 kilometers. So we are trying to understand their aerodynamic mechanisms and to apply that to develop bio-inspired micro-air vehicles.
These Vicon cameras emit infrared rays which will reflect off of these markers, and we can read those markers. When we have a bunch of cameras, it can triangulate those markers to one position in space. You can study the motion or the kinematics of the butterfly and the way it flaps. So this is the CFD simulation, and here we are seeing the vertical activities that is the wing is producing by interacting with the fluid around it.
So is that a vortex that you're showing?
That is vortexes. Those are three-dimensional shapes of the vortex around the wing.
So you're modeling vortex shedding.
Yes.
Using computational fluid dynamics.
Exactly.
And retroreflective imagery from actual biological specimens.
Yes, that's where we were going towards it, yeah.
And the whole point is to make a micro-air vehicle, or at least study the efficiency of the butterfly so that we can understand how to apply that toward a micro-air vehicle.
The possibility of actually using it to do cooler things.
That's rad.
This flapper is hooked up to a force transducer at the bottom, and this measures the force produced by the flapper, and we can see the forces in our software, which is directly connected to the force transducer.
Oh.
So let's do
I don't know why that's so exciting, but it reminds me of those birds. Do you remember the old birds that you could wind up and throw? You're trying to figure out by flapping modes how a butterfly steers.
I'm trying to get the communication between the flapper and our transmitter.
She's trying to develop a remote controller so that she can control something like this.
Are you doing this?
Yes.
This looks like electrical engineering.
A little bit of.
Really? So that's awesome. What year are you?
I'm a junior.
Really? Are you going to be a grad student?
I am going to grad school, yes.
So the whole point of this whole program, Dr. Hazeli, is undergrads can come in and they can work with you on the matrix stuff, the squishing
structure, designing the light structure materials for impact situation.
And that's probably what I'm working on.
Exactly.
So, yeah, and then there's also the ion propulsion and plasma.
That's true, and also we have the project about supersonic wind tunnel with Professor Ligrani, and you have already discussed about Dr. Zhou lab, and
also here in the Atom Lab.
Right, exactly. Students come to the program, they have an opportunity to interact with the more senior students and also the professor to get some hands-on experience about the active research, which is important for education and the government.
This is a big deal. So if you want to check this out, you can go to, you made a website, didn't you?
We did.
What is it?
So it's Matrix at UAH.edu.
Matrix.uah.edu.
Yes, that's right.
You can check it out, work with me, work with Dr. Hazeli, work with Butterfly Wings. Big deal. I'm excited about this. So go to the website, matrix.uah.edu, and apply. And who is it for? It's for transfer students?
For transfer students, basically they get to pay for their education through the NSF money we have. And in return, they need to improve their GPA and be involved with the research. Basically, it's a win-win situation.
So it's not for free. You actually have to work hard and do a good job here.
Well, they don't have to, but if they need to stay in the program.
So yeah, you gotta work hard. Is that what you're thinking, Dr. Kang? Yeah. Okay, cool. Anyway, matrix.uah.edu. That's an NSF grant that Dr. Hazeli is leading up and I'm working on. So go check it out. Thanks.